Hello, I'm Oliver Philcox, a postdoctoral fellow at Columbia University and a junior fellow of the Simon Society of Fellows. During this talk, I'm going to give you a brief insight into some of the work I've been thinking about over the last year concerned with the idea of how to search for parity-violating signals in a novel observable, the CMB temperature and polarization anisotropies. So let's begin by thinking more generally about how to search for parity violation. In this talk, I'm going to be concerned only with scalar parity violation and observables such as the density of galaxies and the CMB temperature and polarization fluctuations. For now, these are our best sources of information about cosmology and will remain so certainly in the near future. For such scalar observables, the statistics we can use to search for parity violation generically involve 4 distinct points. 2 options for this involve the 4-point correlation function, so the galaxies ranged into tetrahedra, as you see on the right-hand side here, or generically, its Fourier space counterpart, the trispectrum, or its harmonic space counterpart, the angular trispectrum. If we're dealing with more complicated observables like polarization or the shapes of galaxies, we can actually have some slightly different statistics. For example, galaxy EB mode shapes would also provide a new avenue of searching for these sorts of signatures. But for now, I'm just going to consider these scalar observables. So let's start by giving a lightning recap of the results obtained from analysis of the galaxy 4-point correlation function. This will set the scene for a lot of the analyses of the CMB I'm going to be talking about later. So what do we do? Well, essentially, we take around 0.5 to 1 million galaxies in the BOSS survey, particularly these little white dots shown on the figure on the left here. And from each of these, we assign the galaxies into tetrahedral shapes, just taking all possible combinations of 4 galaxies. The useful thing about tetrahedra is that they're chiral. Each tetrahedron can be uniquely decomposed as a left-handed or a right-handed shape. For example, you could take the triple product, the red, blue, and green vectors, and assign it left if it's positive and right if it's negative. And this is a rotationally invariant description, which is very nice because we can uniquely separate out rotations and reflections. Once we've done that, essentially the statistics we're interested in are saying, do we see an imbalance? Do we see more left-handed or right-handed tetrahedra in the universe as a function of scale? So I'm sure you've seen the results before, but let me show them here. What we do is we take this left minus right statistic, and then we do some kind of statistical analysis based on it. Astronomers love to do chi-squared analyses, and in this paper, led by myself, we were doing kind of a simulation-based variant of this. And essentially, the idea is to take this 4-point function data, which is very high-dimensional. It's like 1,000 elements in your data vector, all of which are very correlated with each other. I'm going to take this data and compress it down into a single summary statistic. I'll call that thing chi-squared. Basically, this is the data squared divided by its variance, or realistically, including the off-diagonals of the covariance as well. And here I'm not assuming anything about this covariance. Hopefully, it should be a relatively good estimate of the true covariance, but I'm just using this as a data compression step, so it doesn't really matter if I use a slightly wrong covariance. Once I've got this chi-squared summary statistic, what I then do is I make a plot of this from 2048 simulations. This is this thing shown on the blue curve here. Once I've got this empirical distribution from SIMS, I can compare my data to it. The result of this is that I can do a purely simulation-based measurement of whether my BOSS data contains more parity-violating physics than a simulation. Of course, our simulations are parity-conserving, so if we do see the data significantly above the simulations, it could be an indication of some additional parity-violating 4-point function in our data. This is shown in the right-hand side here, and you see that the data is roughly inconsistent with the simulations at around 2.9 to 3 sigma significance. So here we haven't assumed anything about sort of linear theory or Gaussianity, et cetera, but we do have the important implicit assumption that our simulations are actually accurate. Essentially, we assume that our simulations have the correct noise properties to represent the data, and that will be important later. So for a minute, let's assume that this result is true and exciting. The question then becomes, well, what could that mean about cosmology? So here I wanted to highlight a couple of different avenues of new physics that could source these sorts of effects. Generically, when we think about new physics, there's 2 easy ways to find it. in the very early universe or in the very late universe. In the very early universe, we could create such parity-violating signatures through inflation, in particular, novel physics such as novel extra particles, ghost condensates leading to higher order terms becoming lower order, or things like gravitational wave interactions, for example, via Chern-Simons mechanisms. These create asymmetries of left and right-handed gravitational waves and then interact with the usual inflaton to create some kind of imbalance in the distribution of galaxies today. Importantly, any of these mechanisms gives us a robust prediction for what happens in the early universe through a primordial trispectrum, which we can then take and get out a prediction for what happens in the late universe via some kind of linear or nonlinear theory. The conclusion with this is, out of the 18 theoretical models we looked at, these couple of these variants and a whole bunch of variants of different masses, spins, etc., we didn't find any evidence for any inflationary source. Doesn't mean we haven't found one. It just means the data doesn't seem consistent with any of the ones we have looked at. Another option is late universe physics. For example, could we modify gravity? Could we add some kind of magnetic field coupling? To me, these are actually quite difficult scenarios. Generically, any model of late universe physics has to affect the galaxy distribution on ultra-large scales for it to source the sort of effects that we were seeming to detect in the BOSS data. The BOSS data is mostly at scales of sort of 50 to 100 megaparsecs. Down the smaller scales, we consider about 20 megaparsecs. And if you think about it, galaxies have only really moved about 20 megaparsecs from inflation until today in Lagrangian coordinates. So we really need some very large characteristic length scales for our new physics in order to source such effects. And you can quite generically show that these sorts of physical effects are pretty much suppressed, usually by derivatives or loops in the theoretical model. Of course, there's always the elephant in the room. What about systematics? And in this, I think, kind of primary example here is harking back to what we were saying before. Do we understand the noise properties of our data? Are our simulations valid? Or if we use theory, is our theory valid? This is, of course, the pessimistic view, but it's always something we should bear in mind. So how do we resolve this? Well, I think future will bring us a lot more large-scale structured data. We've got DESI, Spherix, Euclid, Roman, Rubin, etc., all of which are going to give us 10, 100 times the number of galaxies we currently observe. And we can do much more high precision analyses with these data sets. But I will just caution that although the statistical power of these data sets far exceeds what we have now, this doesn't necessarily mean that the systematic errors will shrink in the same way. It's entirely possible that if we have systematics in our pipelines now, we might still have them in the future. So this really motivated me to think, can we do this analysis using a totally different probe? And this leads me to the second part of my talk of the CMB. Essentially, the question is, can I do exactly that galaxy survey analysis, but with the CMB instead of the galaxies? What I want to do is I want to draw tetrahedra on the surface of the CMB, or three-dimensional spherical shells, and then look at the parity-violating piece of that. The only real difference is, instead of galaxies, I now have temperatures on the CMB. And later, we'll also consider polarizations. So this has never been looked at before, but it turns out to be possible in practice. So to dive a little bit more into details, what one first has to realize is that what you're really measuring in the CMB is something called the reduced trispectrum. So if you simply take your CMB, just shown on the left, and you take 4 powers of it, and write it in harmonic space, you end up with a whole fancy mess of stuff, involving a whole bunch of weights, things like this, and this little object shown in the blue. This is the trispectrum. It's a harmonic space version of the 4-point function, and it actually has a really nice decomposition in terms of parity. If L1 plus L2 plus L3 plus L4 is odd, this thing is parity odd. If they're even, it's parity even. That's it. There are no other interesting manifestations of parity here. It's a very simple breakdown. So essentially, all we need to do is go into the data, measure a trispectrum, and then just look at the particular modes when everything is odd. We can do that, but it turns out it's required a fair amount of computational, numerical, and theoretical investments to get tools which can actually do that in practice. So I ended up coming up with a whole new scheme called a polybin code, which is the logos, I think, just hidden off the top right there, which basically makes measurements of power spectrum, bispectrum, and trispectrum of the CMB with a whole bunch of fancy features like deconvolving out mask, removing parity leakage, minimum variance weighting, all fun things like this. The point of this analysis, however, is that we can now measure this thing robustly in practice. This is an example of the results. On the right-hand side here, the blue points I'm showing are the 4-point trispectra measured from the Planck large-scale temperature dataset. And in the red and green, I'm showing you the simulations. Here I've done some rescaling so everything can nicely fit onto one plot. But what you see is a whole bunch of points jumping up and down around 0. This is not necessarily the easiest to interpret. So if we actually want to make some measurement of parity, we're going to need to do some statistics, just like we had to do for the galaxy dataset. And what I should say here is that this dataset is pretty nice. Like what I didn't tell you in this last plot is that all of these data points are essentially perfectly uncorrelated with each other. It's a very different scenario to the galaxy one, which they're very super correlated. That's simply because we don't have much nonlinear mode coupling, and doing things in Fourier space or harmonic space gives you some nice properties about decorrelation, which is very useful in practice. So once we're done with this, we can then do our detection significance tests, for example, a chi-squared test. And we can do exactly the same game as before, comparing the data purely to simulations. We could also compare the data purely to theory. And it turns out in this case, it doesn't really matter what we do. We get exactly the same results. In fact, in black here, I'm showing you the theoretical distribution, this chi-squared summary statistic. And in the histograms, I'm showing you the empirical distribution from high-resolution simulations. Very difficult to do this in LSS. These distributions generally look quite different, just because theoretical covariances are much more difficult to compute. In fact, here, I can do the analysis using very simple simulations, which take half a second to compute, and I get basically exactly the same results as if I'm doing things with very high resolution simulations, which the Planck collaboration took months or even years to compute. In fact, that's the difference between the red and the green here. So let me show you the results. The Planck data seems totally consistent with the theory or the simulations. We find no detection of anything weird at 0.5 sigma. Now, to hammer home this point, I want to show you a second data set. This data set is saying, well, why don't we use even more data? We have Planck polarization as well as Planck temperature, so why not use it? This question was brought up to me in a talk by Marisuke Shiraishi back in, I think, March, April, it's in Japan. He said, yeah, sure, let's go ahead and do it. So I spent the next couple of months writing down estimators for the Fourier harmonic space polarized Planck 4-point functions, which turned out to be quite fun. We wrote code to do that, again, in our polybin code. The results are basically shown on the right. We basically can make measurements of the temperature and E mode trispectra. We don't want to use B modes here because they don't tell us about scalar physics. Have a whole bunch of combinations of temperature, TE, TT, EE, etc., etc. And we can play the same games once again. The conclusion at this point probably won't shock you. We detect essentially nothing. The data here is consistent with the theory to within 0.4 sigma in this case. Now, just because we didn't detect anything doesn't necessarily mean we were wasting our time. We can still use this data to get interesting constraints on theoretical models. For example, we said before, new physics in inflation directly sources new physics at late times, directly sources parity-violating trispectra in galaxies or in a CMB. And CMB, kind of a linear relation. This equation I'm showing on the top right is the exact relation between the theory and the CMB. So we just need to basically plug and chug and compute out the theoretical model of interest. We've done this for a whole bunch of models. In general, we didn't find anything. This is just an example on the left-hand side here. See the error bars on the trispectrum in black, and then in blue and green, different theoretical models with sort of very arbitrary amplitudes. This is an example of the actual constraints. You see that the constraints are basically always consistent with 0. This is for interactions of a U1 gauge field during inflation. In fact, in this case, you also see that polarization really helps us. We're getting constraints are about 4 times tighter when we add in the polarization data, as opposed to just the temperature. So one little caveat, I should say, just before we finish, is what about projection effects? So people often like to say that maybe there's a problem here. Projection basically tells us that on very small scales, the CMB looks like a flat plane. And parity could be equivalent to rotation. However, I'd like to argue here that this is not really relevant at all. The CMB is a curved, large-scale distribution. It's definitely not flat, and it's not even thin. Recombination is not instantaneous, which means we have a thickness and a time dependence across this thickness. Furthermore, we're working in harmonic space, not real space. So this logic is quite a lot more difficult to apply here. And in fact, a lot of the models we care about involve a bunch of things like squeezed and collapsed tetrahedra. In this case, we often have one leg of of our tetrahedron, which is very, very long. It could be an internal leg or an external leg, in which case any kind of flat scale limits are essentially broken because we have non-flat scale modes. Empirically, we can also see this works. Our constraints are not just dominated by large scales, which we would expect if everything was being washed out on small scales. If you just look at the error bars on, say, gauge field parameter as a function of scale, we get a very, very sharp decrease in the signal, increase in the signal to noise, decrease in the error bar as we add more and more small scale data. This is expected. Marisuke Shiraishi had some Fisher forecasts back in 2016, which basically showed the same thing. So with that in mind, let me conclude about what we actually found from the CMB. And I should say that the CMB is a really nice probe. As we've seen, it's very Gaussian and it's very linear. We don't have to worry about nonlinear gravitational physics, nonlinear galaxy bias, and simulations being a problem, because even our simple simulations very well represent our data. It's also a really constraining distribution. The CMB contains order 250 times more modes than the galaxy. And this means that if we're interested in primordial physics, it's a much more sensitive probe. All in all, the CMB finds no evidence for scalar parity violation. It's a direct trace from inflationary physics. And if these LSS results we found were primordial, we'd expect to see them at roughly 50 sigma in the CMB. Instead, we find them at less than 0.5 sigma. Of course, these results will only get stronger in the future. With surveys like Simon's Observatory, CMB Stage 4, we can probe smaller scales and get stronger bounds on any of these parameters. So at this point, I think I should conclude to say what we're trying to do is answer the question about whether the universe really is symmetric under the reflections. If it isn't, we could find new physics in inflation or at late times. But late time physics is hard, and the CMB doesn't like new physics. So from my point of view, this is a very exciting line of research, but it seems like the universe may not be in our favor. So I say thank you very much, and I'm very happy to chat more about this, the other things discussed in this talk, either through the rest of this conference, by email, or other forms of online communication. Thank you very much.